Today I'm going to tell you about some of the improvements that we've been making to Redshift over the year, and some of the new cool stuff that we're working on as well, and some future thoughts too. Okay, let's actually move to the next slide. Yep. So we've been working on lots of things since GTC last year. We actually saw the release of Redshift 2.6. This was like a major release. It brought denoising with Optix, ray trace subsurface scattering, light group AOVs, important features like that. And I'm going to go through a little bit of a recap here of some of the features that we added since then that are kind of high priority for us. So first off, we had area light spread. This is like a fake barn door effect that kind of allows you to kind of focus your light in a specific direction. And there were some implementation challenges with adding this. We had to make sure that we did proper multiple importance sampling. We have multiple importance sampling for regular area lights. And this was a tricky one, particularly with volumes. And we also wanted to make sure that we had to conserve energy as well, meaning that we didn't want the light to get too dim if you were trying to create a laser beam, so a really tight focused light. And in conjunction with that, another important feature that we added was a shader-driven global volume scattering. So this means you can now use 3D procedural textures, which are very important for getting complicated cloud shapes, things like that. And I should stress that this was for the scattering component, the actual direct lighting, not for the transmission. Transmission is this kind of fogging effect that you see with global volumes. Now, in order to do this, you actually have to do ray marching. And this is actually something that we want to tackle with Redshift 3.0, so it is coming. All right, and now another important thing that we added with Redshift 2.6 was specular light bending through refractions. So what this is like an important feature for very realistic looking glass and lenses, things like that. And what it is if you have a surface and a light source, and you have say a refractive lens between that surface and the light source, you expect to see a warping effect in your specular reflections. And this was something that we didn't support for some time, and I'm just going to tell you a little bit about why that was tricky. So we have two types of lighting in Redshift. We have something called direct lighting and indirect lighting. So direct lighting is a tried and tested method to get really clean looking lighting. And basically, because you know where all the lights are in the scene, you can concentrate all your rays towards those lights. And with using multiple importance sampling, you can be guaranteed that you're going to get the cleanest possible results while using the optimal number of samples. But it does have a caveat. And that caveat is that because you're specifically shooting rays towards lights, those light rays cannot bend. Meaning if you had a refractive object blocking a light source, you can't bend that ray. So we don't bend that ray, and it kind of makes it look like there's actually a transparent object there, not a refractive one. But normally, most people don't really notice this, and we can get away with it, except for hyper-realistic scenes. So the hyper-realistic way, of course, is indirect lighting. So these are samples that are shot from the surface using a BRDF, and those rays can bounce around everywhere. They can reflect, they can refract, they can be rough, and they can, if you're lucky, they can land on an area light. And what this means is that indirect lighting, because it's like a game of chance, you're going to get really noisy area lighting. So this is the choice that we make. We don't use area lighting for, indirect lighting for area lights, instead we use direct lighting. But there's the problem. Indirect lighting actually looks better for things like lenses. So if we want to solve this problem, how do we do it? I guess the answer is kind of obvious. We try and marry the two techniques together. So what we do is, if we know that a ray is not going to bend, and between a surface and a light source, then we'll use direct lighting for this. But if we know that the ray is going to bend, there's a refractive thing there, then we'll say, okay, we're not going to do direct lighting, we're going to stop that ray, and we're going to let it continue and just do indirect lighting. So you can kind of get the best of both there. And we also have a mixed mode as well, because you want to get, direct lighting is really good for getting very clean looking results. So we have some kind of threshold to say if the surface is rough, or if the refractive object is rough as well, then we kind of blend the two techniques together. And 2.6 also brought cryptomat support as well. This is an excellent technique developed by Jonah Friedman at SciOp. And what this does, it attempts to solve the matte coverage problem. So what artists do is they basically paint like matte objects, like different colors. And what can happen is that when you have like heavy anti-aliasing or heavy depth of field, those colors tend to bleed together. And when you have that kind of situation, it becomes very difficult, if not impossible, to actually do effective comping with that kind of matte. So cryptomat solves that problem because it works at a subsample level, and it also factors in deep as well. Okie dokie. So yeah, also in Redshift 2.6, we did some improvements to our render view. So the Redshift render view is like an ongoing project. It's all about the kind of workflow, trying to make things easier for artists. One of the things that we added was post effects. And one of the first things that we added was photographic exposure and vignetting. Now, any like Redshift users out there know that we've always supported photographic exposure, but the important difference is that used to be like a camera setting. And because it was a camera setting, it meant that if you went and changed any of those like values for your exposure, it meant you would have to re-render your scene, which of course is slow. So we moved that to our render view, and now it's like basically real time. The next thing is that we added like color control and LUTs. So this is like a great thing for getting like final color grade. You can kind of get more kind of atmosphere out of your lighting, like changing the mood. And we also added bloom. Now everybody knows what bloom is. It's that kind of dreamy effect that was overused in like 1960s TV shows, and also overused in like early video games in the 2000s, I think, like flight simulators, which is what I used to work on. But we have like bloom, and we have like lots of control for it too. Looks very nice. We also added streaks as well. So streaks are like a very dramatic kind of effect for like really hot lighting. You kind of get really nice kind of streaks, and we can like control the rotation of them, and we can tweak the tails as well. And also something that was overused in flight sim games in the early 2000s is lens flare. This is also very popular in like sci-fi films when you get a very hot light source, and that kind of light kind of bounces around in like an imperfect lens. It kind of refracts about, and it kind of generates this kind of like cool looking bokeh kind of effect with these like kind of hexagonal shapes. So we've added support for that, and you can like tune how many of these things you have, and you can kind of tune the chromatic aberration as well. And we're also going to be working on a physically based version of this too in the future. So as I said, Redshift render view is all about kind of making things easier for the artists. So we have lots of controls for these new post effects features, but they're like very intuitive as well, very easy to use, but very powerful. And like I said, this is real time. So we're using OpenGL to accelerate this currently, but we also have it supported in batch rendering too. Our batch version is currently on the CPU, but it's like massively multi-threaded, so it's nice and fast. But we want it to be faster as well, so we're also planning on working on a CUDA version too. And we also have a post-effects AOV planned. We actually have support for this right now internally, except we don't actually expose it in the GUI. And so this is going to contain the additive post-effects. And what I mean by that are things like bloom, streaks, and flare. These are the kind of effects that you can just slap on top of your composited render, like in Nuke, for example. All right, so since SIGGRAPH last year, there were some other general core improvements that we did to Redshift. So first off, we started work on improving the volume shader. This is for like basically VDB volumes, things like that. And the first thing that we wanted to improve was add color support. So we added like color channel support, like color ramps, color transmission. It kind of makes your volumes look way more interesting. And at some point in the near future, we're going to be adding a noise feature as well. So you can have like more kind of like fine detail in the noise shader in your volumes. And we also improved like direct lighting cutoffs. This is like a slightly more technical thing. It's an optimization. It was funny before. Adrian was just saying that like when you do less rays, it actually runs slower. Well, this is kind of like part of that, but we think that's actually different. If you do less rays in Redshift, it actually renders faster. But anyway, so what we found out was that we have a feature called cutoffs, and that's like a stochastic way of dropping samples that are deemed unimportant. And what we found was that when you had many, many lights in the scene, the renders looked kind of noisier than what we were expecting, and this came to us as like a bug, basically. Like, why is this so noisy? So our simple answer was just, lower the cutoff's threshold, and improve the number of increase the number of samples, and that got rid of the noise, yes, but it actually made rendering slower. So we realized that this was actually like a problem that we had to solve because Redshift is all about speed. Anyway, when we looked into it, we found that it was a random numbers problem, and this was actually kind of biasing the cutoffs to do things that they shouldn't do. So we fixed that problem, and now we could happily tell the artist that they can actually increase the cutoffs threshold and lower the number of samples, and they get better looking and faster results than they had before. So it was a big win, we thought. In a similar realm, we also improved the importance sampling for single scattering, so you can use like fewer samples and get clean results. And we also added multi-step deformation blur. Now this is something that was very kind of popular with some of the more high-end customers of ours. Now previously we only had like 2 steps of deformation, which is kind of like a linear thing. But if you have like more complex animations, like say if you want to animate over a curve, you need multi-step deformation blur, so we added that. And we also had custom AOV visibility through reflections and refractions. Now what this is we had like a few customers that were trying to create their own mats and their own like masks, and they wanted to be able to see those masks and mats through refractions and through reflections. Now previously what would happen is if a ray hit a reflective object or a refractive one, all that data, all that color data would just get dumped into the reflection and refraction AOVs. Well, that's not what they wanted. So we added support for being able to see custom AOVs through these things. And we're actually going to be adding support for lighting as well very soon in Redshift 3.0. All right, Redshift 3.0. So this is our next big release. Some kind of radical changes are coming to the technology. So we announced Redshift 3.0 at GTC last year, and we even had like a sneaky preview of some of the prototype technology at SIGGRAPH. And what Redshift 3.0 is basically a culmination of some of the more kind of out there ideas that we've talked about over the years for like optimizations and stuff. Like the kind of thing where like Panos would very often say, Rob, I've got a great idea for an optimization, but you're not going to like it. And we've had many conversations like that. And the reason was because it meant that we would have to rewrite huge chunks of the core in order to be able to do this. And really our end goal with 3.0 is to make Redshift both faster and easier to use. So what kind of refactoring are we talking about? So first off, we're refactoring how we're doing ray tracing, meaning how we kind of manage the rays. And we're doing this so we can get like a huge performance boost for deep bounces. So let me tell you about the problem. So the problem is that GPUs are super powerful. And what it means is that you need to give GPUs an absolute ton of work to do to make them really happy, to make them very efficient. If you don't do that, the GPUs are underutilized, and it means they're kind of not efficient, which means rendering actually is slower. So one of the ways we do that today is that we try and give GPUs tons of rays. And we have like a trick in Redshift. We've always had this trick. It's called ray reserve memory. And that guarantees that you can crank up the amount of memory that you're going to use for rays. So you can like try and max out your GPUs with rays. But that doesn't solve the problem of what happens with deep bounces. And with deep bounces, the thing with ray tracing is that as the rays are bouncing around, you tend to spawn fewer rays, some get dropped, and eventually you get very little work happening for those really deep bounces. And what this actually means is that the GPUs are being underutilized and therefore inefficient, which means slower rendering. But we wanted to change that. So we've re-engineered how we batch our rays, how we manage our rays, and what we found is that we've managed to be able to use less memory than we would have had to have used for ray reserve memory, which is indirectly controlled by automatic memory management, and actually get better performance with this technique. So this means that like scenes with like very deep bounces, like lots of reflection, lots of refraction, really deep roughness, those scenes we've seen an actual boost of up to 4 times faster rendering, which is like pretty huge, we think. But not to worry, even simple scenes will benefit from this facelift. We've seen maybe about 10 to 20% improvement on there as well. So another thing that came quite nicely with this, so once we started refactoring the tracing stuff, we realized that we could now increase the trace depth for Redshift. So previously, Redshift had like a trace depth limit of 16, and that's for reflection, refraction, diffuse, bouncing around, and also transparencies as well. Now this is okay for some scenes, but if you want really, really good realistic lighting, it's found that it's not actually good enough, and we've had lots of complaints about this. So it was time to do something about that. So in 3.0, we're going to have like 64 indirect bounces is our trace depth limit. We think that's going to be enough. We hope it is. So this is for reflection, refraction, and diffuse. And we've also decoupled transparency rays from refraction rays so they can have their own trace depth. And this is like super important for like opacity cutouts, like transparent objects, like layered things, and hair, for example, things with great depth complexity. We're going to be giving like 256 trace depth deep. So let me just show you a quick example of why that's actually important. So this shot here has like lots of depth complexity. It's using like Redshift 2.6 with like maxed out 16 trace depths deep. And you can see it kind of looks okay. But actually, to the trained eye, there's something wrong there. You can actually probably see quite a lot of light leaking. And if you look to the top left, the actual complexity of the leaves, it just kind of looks a bit weird, looks a bit wrong. So now you can see why. With 256 trace depths deep with Redshift 3.0, you can see it actually looks, this is what it actually should look like on the right, which is actually very different. You don't get that kind of light leakage, and the complexity on the top left actually looks more correct. Okay. Optix. So we started integrating Optix into Redshift, so late last year. And I guess the question is, why does Redshift need Optix? Now, NVIDIA has asked us for many years about, why don't you use Optix? It's great. And our answer was always, we have our own ray tracer, it's very fast, and it's written in CUDA, so we don't need Optix. But times change, and with RTX and RT core acceleration, Optix allows you to get at that excellent hardware. So we'd be kind of fools to not want to tap into that excellent hardware. So we've integrated Optix. And we're happy we did, but there were some implementation challenges. So one of the things was that we didn't really have time to port all of Redshift to Optix. Everything's written in CUDA, and there's just so much to Redshift, it would take us forever, probably. And also, Optix doesn't actually support all the features that we need. I mean, Redshift is a production quality renderer, and there are some things that out of the box, Optix just can't do. So we had to make a call. And we decided to go for like a hybrid approach. So what we're going to do is we're going to let Optix sort of manage all the, the BVH, the ray trace hierarchy construction, and then have Optix actually do the ray tracing. But everything else is still regular Redshift. So Redshift is still going to generate the rays, Redshift is going to shade them, and it's still going to do the out-of-core texturing. And we actually found that it was, this actually was not that difficult to implement. I mean, Panos, you might want to talk about this later if people ask, but we actually managed to add like a very thin layer between Redshift and Optix, so that worked really well for us. But one thing that we wanted to do as well, which is like a bit of a challenge, was try and be able to sort of mix non-Optix hardware, like the older generation, like Volta, Maxwell, Pascal, with RTX hardware. And basically what we found was, and don't hate me, John, that the Optix ray tracer for older generation, like Maxwell, was significantly slower than our CUDA-based one. So we decided that we're going to use like regular Redshift tracing, like with Redshift CUDA tracing for like non-RTX hardware, and we're going to let Optix do ray tracing for RTX hardware to get at that RT core power. And more specifically, we're going to do that if we know the scene is going to fit in memory. I'm talking about the geometry here because we don't currently support out-of-core geo for RTX. So the initial results. So we flicked all the switches, we turned everything on, and we were very happy to see that just ray tracing alone, we saw 3 to 5 times faster performance than our CUDA ray tracer on RTX, which is pretty huge. These were the kind of numbers that we were hoping for, and when we got them, we were very, very, very happy. And I know this was discussed before in the other talks. You know, when you're talking about rendering as a global kind of problem, a total problem, like maybe 50% of that is ray tracing with production scenes, and maybe 50% of that is like the shading and the texturing. So while we might not expect to see 3 to 5 times faster rendering in total, we do expect to see some good results just from accelerating the ray tracing itself. And with the Redshift benchmark, our initial tests are showing about 23% faster using RTX, which we think is a pretty good win. So we ran a few like benchmark tests. So first of all, we were basically trying to let's see if we can mix some more complex shading and maybe slightly less complex geo and see how RTX performs. And we found that it performed about 1.4, 1.5 times faster than our CUDA ray tracer, which is pretty nice. And then we tried to like crank up the settings, basically. So this is like a UHD image, and it's a shame you can't actually see the true detail there, but all that is grass. The whole thing is like billions of grass. And this kind of geometric complexity is where the RTX really starts to shine. You know, it can just chew through those polygons like really, really fast. And it was actually 1.75, 1.8 times faster than our CUDA ray tracer, which is like getting impressive. And with this one, maybe slightly simpler shaders, but huge depth complexity and another like a very high resolution image. And then RTX just basically destroyed our CUDA ray tracer, and it was actually more than twice as fast to render this scene, which is like massive. So we're thinking that, you know, with the better ray batching, which is coming in 3.0, and couple that with RTX acceleration, I think that was a GTX 2080 as well that we saw this. We're talking about crazy rendering speeds with Redshift 2.6. So not quite Optix related, but still cool NVIDIA hardware related. NVLink is something that we've been wanting to support for some time. NVLink is now in consumer grade cards, so that's kind of nudged us to actually like take action. And for any of you that don't know, NVLink is a really nice piece of hardware that allows you to connect 2 GPUs together, so one GPU can read the other's memory like really fast. So we're going to be using this to not double the memory necessarily, but maybe double our cache. And I'm talking about like geo and texture cache in Redshift. So this, we suspect, is going to give better performance for like those really kind of heavy scenes that would ordinarily go really out of core. So we're excited about implementing that. Okay, so the second like overhaul, the second refactoring effort was for the shading system. And I don't know if you can probably guess why. So we're going to be coming up with a shader SDK with Redshift 3.0. We've been talking about this for years, but it's finally happening. I'm going to talk a bit about that next. But other than that, we wanted to add something we call automatic sampling. So what is automatic sampling? Well, automatic sampling, you can think of it kind of like our primary ray unified sampling, but for shaders. And I'm talking about for reflection, refraction, diffuse, trying to clean up that noise very, very simply. And really, you know, the goal is to, like I said with 3.0, is to make things simpler for artists and faster rendering as well. So, you know, when you have like all these assets, you've got all these materials, you've got all these lights, and you're trying to like pinpoint where the noise is, and you can go in there and you can tweak your number of samples on your lights. That's like a huge pain. It's very trial and error. It's very time consuming, and you might not even get, then you have to try and render it to see if it actually works, and you might not get the results you want. There's all this kind of back and forth, and it's really cumbersome effort for the artist. So we want to take away that pain with automatic sampling and let Redshift actually figure out what to do for you. So using the noise threshold of the primary rays, unified sampler, we're going to be generating like smart noise metrics internally to try and determine how many samples you ideally need for each of these effects for like, reflections, refraction, diffuse. And, some of our initial tests give us actually better performance as well. So we're really pleased with that, because what you can do is when you're trying to do it yourself, you might actually use too many samples. Oh, it looks clean, but it's actually rendering slower than it should because you've used too many samples. Well, with automatic sampling, we're trying to like avoid that problem. And also, we're going to be improving cutoffs as well. So as I was talking about cutoffs with direct lighting, we have that for shaders as well. And the idea is that you want to try and like stochastically drop unimportant rays to try and speed up rendering. Now this works like most of the time. We use like basically the albedo and various importance factors from like historical information of the ray to try and like drop these rays. But the problem is that maybe like every now and again you might end up with like a really kind of dim surface reflecting a really hot light source, and you might end up there with some really nasty noise that's really hard to clean up. So with automatic sampling, because we have all that information, we're going to be improving our cutoffs as well, so we don't actually end up going down that wrong path of dropping things that you don't think are important. It's actually going to know what's important for real and not drop those things. So ultimately, that's going to result in faster, cleaner rendering. Okay, the shader SDK. All right, so like I said, we've been talking about this for years, and finally it's time to actually do it. So one of the reasons that this has taken us so long to actually do is because, like I said, it's like we knew it would involve a refactoring, but we also wanted to like actually think about how we were going to do this, because Redshift is like very complicated internally. There's lots of power, lots of things you can do, and shaders as they're written today expose all that, and it's very complicated to write shaders. So we wanted to have to think about what kind of shading language could we like come up with, what should we have to make like writing shaders really easy but still be able to get at that kind of like that power. So this involved like a major kind of refactoring effort on my part. Basically the last 3 months, this is all I've been doing, rewriting this stuff. And really the goal is to, like I said, to get rid of any kind of redshiftiness from the shader language, to try and hide all that inner working, all that kind of ugliness, like, point-based light. How do you differentiate between point-based lighting and ray trace lighting? And what do you do about cutoffs and like Russian roulette and all these kind of like crazy optimizations that we might have in there? We wanted to try and get rid of all that horrible stuff, and it's still there, but you just don't see it. And while we were working on this, we actually realized that there was it opened up some opportunities for us, some really cool opportunities. First off, we realized that we could actually improve our material blending technology. So just to explain, what we have right now is we have like a 7-way material blender shader, and each one of those materials is kind of for itself. And what I mean by that is that if you have a material that has like refraction, and if you have and you're trying to blend that with a material that is like opaque, what you're going to get is that the refractive material is actually going to shoot refraction rays. And what that kind of actually means is that it's kind of a non-intuitive way to blend materials. We've had lots of artists saying, I don't understand, why does it do that? And we're like, sorry, that's the way it works. So we want to change how we approach this kind of thing. So we're thinking that what we're going to do with 3.0 at some point in the near future is to have more like a material layering system instead of like straight up blending. What I mean by that is more like a kind of a Photoshop style layering, so that you can just like tweak the alpha, and then you can actually blend like stuff like something that's transparent on top of something that's opaque, so it looks like it's actually sitting on top of it and not actually tracing rays, if that makes sense. And while we're thinking about this on another kind of level, how do you do like energy conservation between blended materials? How do you treat those layers? Like for example, if you had like a decal that's kind of glossy, it's got some reflection, it's also got a bit of transparency, you want to kind of blend that with some opaque thing underneath. How do you factor in that kind of the kind of Fresnel effect that you would get from the reflection, so that it doesn't add too much light on the guy underneath that you're trying to blend with? Today, you have to go and use like a, I don't know, a Fresnel shader to like pipe that into your kind of blended material weight. And there's all sorts of things that you have to do, which is kind of cumbersome, I think. So we think that we can probably make that automagic with Redshift 3.0. So we're pretty excited about that. And another thing that we want to do is actually have like nested material blending. That's something we can't do today. So all these kind of things, they kind of open up all these kinds of features that we're going to be like working on. And hopefully, with all this, we're going to get better performance as well. Because just simplifying the shaders alone and moving some of that ugly work that was actually in the shader code means that you can kind of like defer that. It becomes like, you know, more coherency with the code and everything. It's just going to make it better and cleaner. Okay, so the big question is, what is our shader SDK going to look like? So we had a kind of a debate about this. Our original idea was that we were going to come up with like a shader SDK that uses our own kind of language, our own terms, and then we were going to maybe support like OSL and MDL. And the more we kind of like start thinking about what our language should look like, the more we realized it actually starts to look very much like OSL. So what we're going to do is our first target is going to be OSL support, but we're going to be adding some extensions. Kind of things like we want to be able to have like lens shaders, for example. And we also want to add our own closures. So we want to be able to support pretty much all the things that OSL does, hopefully eventually. There might be some tricky ones like differentials. They look kind of tricky to do, but we're going to be supporting, you know, all the kind of noise shading, like procedural shading, closures, all those things we know we can do. So that's going to be what our first step is going to be. And once we've done that, other things start to fall in place. It becomes very easy. Like MDL support, you know, this is a really, really nice material definition language by NVIDIA. It has cool things like LOD as well, so you can like basically switch your rendering quality. And then also, maybe in the future, we'll maybe tackle Material X. It's very nice. Some big studios are using it, but we want to see if it catches on before we like jump on that ship too. And there are some other cool features with 3.0 as well. More optimizations. So adding 256 trace steps for like deep transparencies, it might impact performance, but we already have some ideas about how we're going to like solve that. So we're going to be optimizing specifically deep transparencies. It's kind of like a radical way of thinking in the renderer. It's again, this is part of the core rewrite, which is why we haven't done it yet. But this is going to become easier with Redshift 3.0 to get better performance for that, which is going to be very important for things like hair, cutouts. Right now, if you want to have like very deep, like say opacity things, you have to use the sprite node, but the sprite node is limited. You can't use UDIM for a sprite node, for example, and you can't have like semi-transparency either. But all this is to say that with the 256 trace steps deep and this optimization coming up, then we might even be able to like ditch the sprite node. And also the many lights thing, so talked about cutoffs. What we want to do is like try and solve the problem of like how do you render efficiently when you have many, many lights in your scene. So try and imagine you have like a city block. You have like full of skyscrapers. Each one of those skyscrapers has hundreds of lights in them, and you have them all over the place. And so what you have there is lots of like horrible situations with indoor-outdoor kind of like lighting where lots of that lighting is going to get blocked, and it just becomes very slow to render. And right now, Redshift is kind of dumb. It doesn't know about walls and things like that in skyscrapers. It doesn't know about these blockers. So it's just going to try and shoot those rays, and those rays are just going to get blocked by those walls, and it's just slow. So this is going to be like a heavy kind of R&D effort on our part. We have some really good ideas about that. And once we started like fleshing them out, we realized that maybe if we solve that problem, maybe we can have unbiased rendering quality in Redshift, but with biased rendering performance and biased flexibility. So this is something that we're kind of like realizing as we're talking about this future optimization. And of course, when you have that, you have ray trace caustics, which we think is going to be like just a huge win. So very exciting times. All right, so there's always more stuff coming as well. in 2.6 and 3.0. So first off, we're going to be having a USD support with like Hydra. That's coming probably in the next couple of weeks. A lot of people are asking about the Intel denoiser. It's a similar denoiser to Optix, but this runs on the CPU. Very easy to implement, apparently, and we just want to give users more choice. So we're going to be hopefully adding that soon as well. And also light blockers. With lots of requests for this really cool, useful feature. We kind of have to put it on the back burner while we worked on Redshift 3.0 technology, but we're going to be bringing that back up to the forefront pretty soon as well. Random walk subsurface scattering. With all the kind of work that we're doing with Redshift 3.0 and making the ray tracing more efficient, this kind of makes random walk subsurface scattering like more feasible for us too. And also volumetric multiple scattering. Right now you can only have like one bounce in your volume, and the only reason we do that is because of performance. But with the better performance with the tracing and RTX, we're going to be able to add like a trace depth for volumes as well to get like multiple scattering, to get like really nice looking volumes. LPEs. This kind of goes hand in hand with OSL, which needs LPEs. There are no special commands, no special shader commands in OSL to like write out AOVs, so we need to support LPEs, and this eventually will complete our suite of custom AOV technology. And also toon shading. This is one we've been talking about for some time. It's kind of a tricky one because toon shading is, lots of studios have different needs. It's a very stylized kind of thing. So we're talking to lots of different studios to try and find out, like, what can we get like a best of everything so we can have like a shader that kind of satisfies everybody. So that's something that we're working on now as well. And possibly with the Redshift SDK, the shader SDK, you might be able to write your own more complex, more customized toon shaders as well. And then distributed rendering. We talked about this one for a while as well. This means essentially that you can do rendering on, say, a laptop or something. It doesn't even necessarily have to have like a powerful GPU in it, and you can just send that data to like the cloud or like a friend's machine or somewhere else on the network. And we want to be able to do this like really, really super efficiently. So this is something that we're going to be working on as well. Okay, the future is bright. Okay. We're working on a Blender integration. Blender seems to be getting more popular. Everyone's asking about when is Redshift coming to Blender, and then we're like, never. But we've changed our mind. So we're working on a Blender integration right now. It's getting there. And hopefully we'll have something maybe in alpha, maybe in like a few months, probably around about SIGGRAPH time. The other thing is that we want to talk about like speed. NVIDIA's always bringing out cool new hardware. GPUs are getting faster. You get things like RT cores in RTX, which kind of change the game. And it just makes rendering faster and faster. So Redshift is all about speed. And one of the questions we've been asking ourselves is, can we get Redshift to be real time? Well, we think we can. So we're actually working on a real-time version of Redshift. I know RT is not very original. Come up with like a cool name for it. I don't know, maybe someday like a code name, but we haven't got one yet. So this is a new renderer. We've got a new rendering team working on this, and we're going to be utilizing like a mix of like gamer technology, DXR for like super fast tracing, and we're going to be utilizing our like years and years of experience in the video game industry, where we know all about real-time rendering. But more importantly, this is going to be fully integrated into the DCCs like Redshift is today. In other words, our plan is that the artist is not going to be aware that it's a different renderer. They're just going to be aware that it's rendering faster. So it's going to be like a simple little switch. Do you want to use like production quality Redshift, or do you want to do Redshift real time? So no compromise on the actual features of the DCC. It's going to be fully integrated. So we're very excited about that, and we're going to be talking more about this new product around SIGGRAPH time. Okay, that is me done. Thank you very much. Yeah.